Yeah, we've talked about the relative motion already. So then let's go through the forces. I think we have talked about a bit of the forces before, but not much, most likely, not much. So this time, then let's go have a look at. Uh, in my record, okay, okay. So the first one, okay, then let's introduce Newton's law of motion. Newton's conclude three laws for the motion. And then it says that okay, all all the theory of the force is based on the Newton's laws of motion. So let's have a look at the first law. So it says that if there's no net force acting on an object, the object will remain its inertia. So what does it mean? It means that if the object is initial at rest, that the object will remain at rest. But if it is initially moving, then the object will continue moving with the same constant velocity. So that means if the same constant velocity, that means it will finally move along a straight line. Okay. Because constant velocity, that means a constant magnitude and also constant direction. So that means the direction of motion does not change and it move along the straight line. Okay, so and then let's go through the second law. Okay, Newton's second law. We don't do the exercise. Okay, I think you understand the concept behind. It's not too difficult. Maybe. The few time we still need to explain later on. So what does mean by net force? I think you have the concept of the force. So force, we say that force is the cause of the motion. But to be precise, okay, force is the cause of the change in motion. Whenever you see the motion has some change, so that means either it is moving faster, slower, or changing direction. It means there should be a force or a net force acting on the object. Roughly speaking, okay, we net force is just the vector sum of all forces. But we'll go through the net force after introducing the Newton's second law. So for the Newton's second law, the formula is quite simple. Most likely you learn it as net force u ma. But actually, Newton states Newton's second law as change in momentum over change in time. But let's omit this one first, and then we will talk about these two the difference between these two later on. After we introduce the concept of momentum. But bear in mind this one is more in general, and MA is the one. FUMA is the one is a special case only. So this Newton's second law tells you how we relate the mass, acceleration, and the net force. So most likely, okay, it's very simple. Okay, given that the mass does not change, and if the net force is larger, the acceleration is larger. That's why we say that the force is the cause of change in motion. But something quite weird is like, so let's say if we say that if net force is zero, okay, then from this formula we can see that the acceleration is zero. Okay. So acceleration is zero. That means the acceleration is defined as change in velocity over time, change in time. So then that means the change in velocity is zero. So that means there's no change in velocity. Then what is the difference between the Newton first law and the Newton second law? It seems that Newton first law is just a special case of the Newton second law. then why don't we just omit the Newton first law and just directly state the Newton second law? The reason behind is we define the force. Uh, we define the force by using the Newton second law. Uh, well, sorry, we define the force by actually we are defining the force in one thing we call the uh, inertial reference frame in the Newton first law. So we can't define two things in one formula. You understand what I mean? And then we just can define one thing from one formula. So the Newton first law states that there exists a reference frame. We call it the inertial reference frame, such that the Newton first law is valid. So this also implies that there exists the non-inertial reference frame. If something is always true, then we know we don't need to define it. That's one example for you, okay, for the non-inertial reference frame. So let's say the car is uh, let's say there's on the on the smooth ground of a car, there is a ball. So everything is smooth, okay. So let's say when the car is accelerating. So how is the ball's motion if you're looking inside the car? There's smooth. That means there's no friction. Then there's no other forces that can affect the motion of the ball. So when the car is accelerating, okay, the ball will just remain at rest. So when you're looking at the ball inside the car, it seems like it seems that the ball is accelerating towards you. But you can't find any net force acting on the ball. There's no friction. All the forces are balanced. So in the frame of the car, the Newton first law is not valid. And then this frame is called the non-inertial reference frame. Okay, because even though there's no net force acting on the ball, but there is a acceleration of the ball relative to you. So I think it may be a bit complicated. Okay, just forget about it. Okay, uh, uh, just remember. Okay, how we can apply the Newton second law. So then let's go to have a look at what does mean by the net force. So net force is a vector sum of all forces acting on that object. So what does it mean by on that object? Uh, so let's say there are two objects, okay, A and B. If you want to find the acceleration of object A, if you want to find the acceleration of the object A, then what you need to include in the new net force? You just only need to include the forces acting on the object A. F2 is acting on object B. Of course, you should not include this force to calculate the acceleration or the net force of the object A. Okay, so this is what we mean by the net force. And then, so what does mean by vector sum? We have learned about the vector. We have learned about the addition of the vectors, and the vector sum is just uh, the sum, the addition of the vectors of force, and then by the triangle rule or whatever rule. So let's give you some examples, okay? So this is on the page 6, and then we are going to find the net force of the following cases. So 1 and 2, lah, Newton is a unit of the force. I didn't give write it down on the before. So Newton is a unit of force. So for the first one, I think obviously you know the net force should be 1 Newton. Okay, you add these two together. If you want to draw the vector diagram, okay, then you can draw it like this. So this is a 4 Newton force, and then this is 3 Newton force. And then what is how we add these two vectors? Okay, do you still remember? So if go from the end, sorry, go from the starting point, and then to the end point. Then this is the addition of these two vectors. Okay. Another thing, obviously, you can see is it has the magnitude 1. And then for second case, the second case I think is the most easiest case. Okay, so when you add these two together, you get 7 Newton. Okay. Then for the third case, remember you can use the triangle rule or parallelogram rule. If you are using the parallelogram rule, just draw a parallelogram. And in this case, this is a rectangle. And then starting from this point to the uh, opposite vertex. Okay. Or you can use the triangle rule. So this is 4 and this is 3. And this is 5. Okay. Similarly, for the case number 4, then the net force can be, okay, what you can do is, okay, this is 4, and using the triangle rule, it's always easier for you to use the triangle rule. Because you can form a triangle, you can just form one simple triangle. So I want to give you some time, and then can you tell me the magnitude of the net force? So maybe just give 1 or 2 minutes. So let's continue now, okay? Now you can either use cosine law lah, do you still remember the cosine law? So let it to be x, okay? For cosine law, you can write it at this angle in between these two lengths is 120 degree. So x squared is 4 squared plus 3 squared minus 2 times 4 times 3 and then cosine 120 degree. Right? Then you can solve the x. You get square root 37. It's around 6.08, is it? And then another method to do it is to decompose the vector phi. And then to decompose it, and then you can get a horizontal component and a vertical component. Okay, do you remember these two orange vectors add up together is equal to the vector phi? And then the horizontal one is just 3 cosine 60 degree. I think it's 1.5, yeah. And then vertical one is 3 sine 60 degree. It's 3 root 3 over 2. Okay. And then you just use the Pythagoras theorem. The horizontal is a 5.5. The vertical is 3 root 3 over 2 and then square. And then you can always get the same answer. Okay. So similarly, for this case, for the exercise 4, either way can do, okay? Either way can solve the question easily. But let's say for question 5, I think it's always easier if there are more forces in different directions. It's always easier for you to use the components method. So you decompose all the forces along the horizontal axis and also the vertical axis. So let's say for the 5 Newton force. So this one has a length is this has a component 5 cosine 30 degree. And this has a component that is 5 sine 30 degree. And then for the 3 Newton, okay, this is 3 sine 60 degree. And this is a 3 cosine 60 degree. Okay, then okay on the along the horizontal there are three forces. Then just calculate the sum with the sum, and you need to see you don't know if you don't know whether which one is larger. Okay, whether the left hand side is larger or left right hand side larger, it doesn't matter. uh, if you calculate a so let's say if you consider the right hand side is larger, but if you finally calculate a negative value, then that means it's on the left hand side. But in this case, okay, the sum along the horizontal component will give you 1.17. And then for the vertical one, okay, for the vertical one, it's almost it's very small. So it's 0.0981. Okay, it's very small. And then then you use a Pythagoras theorem. Okay, then you can find the answer. I'll just skip this part. So these are the example for you how to calculate the net force. Okay. Then let's go have a look at these examples. Example one, now, in equilibrium is another wording for net force 0, 0. In equilibrium, that means net force 0, 0. And also net moment equals 0, but we'll talk about no moment next lesson. For net force 0, 0, okay? For net force 0, 0. So how can you do it, okay? Actually, there are two methods to do it. The first method, okay, you can decompose a component. This is 10 Newton force along the vertical component, vertical side. This is the horizontal component of the 10 Newton force. And then, okay, by considering the net force equals 0, so that means there's no net force, and then the upward forces should be balanced by the downward force. The left hand side force should be uh, uh, balanced by the right hand side force. So this component should have the magnitude that is 6, and this one should equal to F. Okay. Then by looking at the 10 Newton force, okay, you know the component has a magnitude 6 and F, and then so that means you can use the Pythagoras theorem. Then you can easily get the answer 8. So this is the first method. The second method to do it is like if you combine, if you still remember, if you are using the head to tail method, if the vector sum is 0, then the vectors can form a triangle. So that means these three vectors can form a right angle triangle like this, okay? And then you can directly apply the new Pythagoras theorem and then can get the answer very easy. That's it. Okay. Then we skip the example 2. And for example 3, and we'll go through it later on. Then let's go have a look at the Newton's third law. Now this is the law, I think you have learned it in junior form science, maybe. So we have another name for it. So this is called the law of action and reaction pair. So in this law, it says that the forces appear in pair. If object A exert or acts a force on object B, the object B will act or exert an equal in magnitude but opposite inertial force on object A. So that means all the forces are in pair. So if there exists a force that is acting on A by B, then there also exists a force that is acting on B by A. Okay, these two are in pairs. So now this is the condition for action pair. or the criteria for actuation pair. So for the properties of the actuation pairs, okay, they have the following properties. Uh, there is something in common. So they have the same magnitude. They are the forces of the same kind. So what does it mean? So let's say one of it is like the weight, and another one is also the weight. It can't be the pair that one is the tension or another one is the friction. They should be the forces of the same type or same kind. And then they appear and disappear simultaneously. So if A exert a force on B, then at the same time B exert a force on A. If A withdraw the force acting on B, then the forces acting on A by B will disappear simultaneously. Okay. Then the third one is the line of action. So what is line of action? So let's say if B exert the force on A at this position, okay, at this position. So there's a point where the force exerts on. And then A also exert a force at this point on B, and such that when you extend these two forces, they can form a straight line. Okay, so they are acting on the same line. This line we call it as the line of action. This line. Right. So the difference is, uh, they're opposite in direction. They're not in the same direction, and then they are acting on different objects. So that means is one is on A by B, and another one is on B by A. Okay, so these are the similarities and differences. So the examples of the actuation pair is like the following. So the gravitational force between the big M and small m. So no matter it is, let's say this is the Earth, and this is the Moon. Moon exert a force on Earth, and also Earth exert a force on Moon. Let's say for uh, let's say for the Sun and the Earth. So the Sun exert a force on Earth. The Earth also exert a force on the Sun. But if you compare, let's say for the Sun and the Earth, these two forces have the same magnitude, but in opposite direction. Now the mass of the Sun is 2 times 10 to the power 30 kilogram. The mass of the Earth is around 6.98 times 10 to the power 24 kilogram. So it's almost uh, more than 10 to the power 5, okay, larger. And but they have the same magnitude of force. So let's say if you are using the Newton's second law, and if you look at the acceleration of the Sun and also acceleration of the Earth, because the mass is differed by 10 to the power 5, and then the acceleration, okay, we also differ by 10 to the power 5, the order of 10 to the power 5. So that means the acceleration of the Sun times 10 to the power 5 is roughly the acceleration of the Earth. So acceleration on the Earth is much larger than the acceleration of the Sun because of the mass. So that's why in most of the case you omit this force, okay? You just ignore this force, because the acceleration or the effect of the motion on the motion of the Sun, it can be negated comparing to the acceleration of the Earth. Okay, after introducing the three the Newton's law of motion, then we can go to introduce different types of forces. The precise definition is a cause of change in motion. So it can be either be a push or pull, and then the force can either uh, uh, cause an object to accelerate or decelerate, or change the direction of motion, or to deform. I think the picture gives you the concept behind. And then there are three elements of a force. What do you mean by three elements? So that means three elements. So a force, a make up. No, how can I say it? To define a force, okay, uh, you need to specify its magnitude, its direction, and also its points of application. So magnitude and direction, I think you understand it well because it is what a vector quantities have. So you know a vector have the magnitude and also the direction. So force is a type of a vector, so it also has the magnitude and direction. But what does mean by the points of application? So let's say if you consider these two different cases. So they have a pair of forces acting on the same on the identical object. Uh, these pair of forces they have the same magnitude and same direction, is it? So what does mean by direction? To the left, this one is to right, this one is to right. So they have the same direction, no matter which point they add on the object. But you can definitely see the motion of these two objects are different. The one on the left hand side will be at rest, but the one on the right hand side will rotate. So they have different effects on the motion of the object. So this is about the rotational motion, or you just say turning effect. So we'll go through this after this chapter. It's about the moment or the talk. So right now we just omit this part. Uh, by considering all the object as a point. Okay, so right now in this chapter we just consider all the object as a point mass. So if you consider all the object as a point mass, then uh, you know a point does not rotate. Even if it rotates, you can't see a significant difference. So you just can consider, uh, then we can just ignore the rotation motion of the point. Then we just focus on the translation motion of the point. There are different classification of the forces. So I think in your Form 2 uh, IS, you just classify as the contact force and non-contact force. So for contact force, this is a force that exists when the two objects are in contact. I think one of the very common example is a friction. So if the two objects are not in contact, there's no friction. For non-contact force, there are many examples. So let's say the weight. Even you jump and you're floating in the air, there's still a weight acting on you by the earth. And let's say for magnetic force and also the electric force. Okay, so this is the first one of the classification of the forces. So the second classification of forces, all the forces can be classified into four different types. The first one is called the gravitational. and then electromagnetic sum, electromagnetic, a strong nuclear force, or just call it strong force, and then weak nuclear force. So all forces can be classified into these four groups. Strong nuclear force and weak nuclear force only exist in the subatomic scale. That means there's a scale. This is the scale less smaller than an atom. So that means in daily life, you can almost ignore these two forces. And then for gravitational force and electromagnetic force, they exist in a larger scale. That means in the scale of our daily life. For gravitational force, actually there's only one example. It's the weight. And actually all other forces are different forms of electromagnetic waves. Sorry, electromagnetic forces. So all other forces, including the new friction, including the tension, air resistance, water resistance, and so on. So that means actually most of the forces are electromagnetic force. And we can talk about this later on. We can after introducing different forces, then you will know why uh, we say that they are all different types of electromagnetic force. So the first one is the weight. Uh, so you see for my notes, okay, I just give you the details of the direction, magnitude, and also the points of application, and also its nature. Nature means the you may say the origin of the force. Okay, so where does the waste come from? So the waste is a gravitational pull on the object by the Earth. So what does mean by the Earth? So when we are saying by the Earth, it means the entire Earth. Okay, entire Earth is attracting you. This is the attractive gravitational force acting on the object by the entire Earth. Okay, so even you okay, yeah, that's it. Then the direction is always towards the center of the Earth, and then the magnitude of the weight. So W equal mg, and then so this W is the weight, m is the mass, g is the gravitational acceleration. That's 9.81. Now let's see how we can derive this formula. Okay, so first consider an object of free falling in the air. Oh, sorry, uh, free falling. Uh, Maybe you can, let's say, in a vacuum chamber. Okay, in a vacuum chamber, because I want to ignore the effect of air resistance. So if the object is free falling like that, uh, the only force acting on the object is the weight of the object. Is it? I think you can't think of other forces acting on the object. Then by using the Newton's second law, the net force equal ma. Because the weight is the only force acting on the object, so the weight is the net force of the object. You don't need to do the addition because there's only one force. So we use the weight, use a symbol W to represent the weight, and mass, and the acceleration. We know that the acceleration due to free fall is g, so we just replace the acceleration by g. Then we have derived the formula Wmg. Okay, it's derived from the Newton's second law. So in this formula, it tells you the difference between the weight and the mass. I'm not going to talking about this in deep, so you just have to look it by yourself. Weights and mass are different quantities in physics. So weight is a vector, but the mass is a scalar. And the weight is a measure of the gravitational force acting on you by the Earth. And mass is a measure of the inertia or just measure of the matter, the amount of matter. The mass does not change with the place, but the weight will change with the place. What does it mean? So, if you are going to the Mars or going to the moon, the acceleration due to gravity will change. So let's say for the one on the moon, so it's about one sixth of that on the Earth. Okay, so the formula will look like this one. So if you are living on the moon, uh, you can jump higher. Okay, then you can get a gold medal in Olympics most likely. Uh, you can lift objects with larger mass because a larger mass object, because the g is smaller. Okay, by the formula WmG, you can use the same amount force because g is smaller. The m same amount w, same amount force to lift up a large object with larger mass. So the weight is the most simplest force among all different types of forces. So the second easiest is the tension. So tension is the attractive intermolecular force when the string is stretched. I can't explain in details why it is a electromagnetic force, a type of electromagnetic force. You may have learned it. Sorry, you may be going to learn it in chemistry. So there are many intermolecular forces in chemistry. So like dipole, Van der Waals force, London force. But the idea behind is like this. Okay, so let's say there is a rod or a string. So when you extend or when you apply forces on both ends, why it does not break? Why can it withstand the force you applied? So the reason behind is uh, why the particle will not just break down, or the why the bonding does not break down, because there's a attractive intermolecular force between the molecules or the particles in the string or on the rod. This particle wants to uh, stay with the neighboring particles, even though even though you apply the force on it. So there is an attractive force, and this attractive force is the origin of the tension. Okay, so tension is the attractive force when you stretch something. It need not to be a string. It can be a rod or anything. Okay, anything. Okay, that is the meaning of tension. So the direction of the tension is a pulling force because it's an attractive force. Uh, so let's have a look at some of the example. So let's say for example one, you are pulling the object B and to accelerate to the right, and then so how about the tension? There's a string in between object A and object B. So the string will be stretched when the object start to move, and then so there is exists a tension in the string. So the string will exert a force on the object A and also the object B because the string is attached to object A and B. The force is a pulling force. So what does it mean? So that means the tension acting on the object A is pointing away from the object A. The tension acting on the object B is pulling away from is from the object B. So this is a pulling force. Okay? So it is what it means by pulling. Okay, I hope you understand it. Okay, so can you draw the tension for exercise 2? The tension acting on object A and object B. Done. Or you may state the direction in the Zoom chat. The tension acting on the object A is away from object A, so it's upwards. Okay, same as the tension acting on object B. So you need to know how to indicate the uh, how to find a indicate the direction of tension. So it's very important because most of the question have the string on it. So then let's have a look at the case one. So let's say for the string is strict, light, and or massless. So what does it mean by light? So that means the mass is very small, or massless. So in most of the case, unless stated otherwise, okay, all your questions will consider mass as the string has no mass. Then the tension of the string at any point equals. So like in this case, okay, in the case of exercise one, so let's say if the string has no mass, this string has no mass, then this tension acting on the object A has the same magnitude as the tension on the object B. Yeah. So they have the same magnitude. They have the same magnitude. And then for the tension of the string, then how we can derive it, okay? So in the statement, okay, in the statement we say at any point, okay, at any point, they have the equal magnitude. So I draw a string and then I cut the string. I just cut out a very small part of the string. Okay, so that and then at this point, okay, let's say this point B. So at the point A and point B, there are tension acting on these 2 points. So at the point A, the tension T1. At point B, the tension T2. So these are the tension. So a T1 is the tension exerted at this small part by the string on the right hand side. Okay, this is the tension of T1. T2 is the tension acting on this part by the string on the left hand side. Do you still remember? I told you to consider, but to use the Newton's second law. Then we need to have the net force zero and net ma. We only consider the forces acting on the object. Okay. If you consider the string on the right hand side, yeah, there is there's also a tension exerted on the right hand side by the small part. But this is the tension acting on the right hand side, not on that small part. But right now we just consider the forces or the net force of the small part, so we don't count this one. And you should also know that these two forces are actuation pair. This one is on the small part by the right hand side string. This tension is on the right hand side by the small part. Okay. So by Newton's third law, they are actuation pair. So they should have the same magnitude but opposite direction. Okay. Then let's move on. So then there are two forces T1 and T2 acting on this small part. So let's assume that the direction to the right to be positive, and then we can write the net force to be T1 minus T2. Now it doesn't matter if T2 is larger than T1. If T2 is larger than T1, if you get a negative value, so that means negative value, that means it's on the left hand side, on the opposite side. So then equal to MA. This is a net force here, MA. This M is the mass of this small part. Okay. Then because we set the mass, okay, because we set the mass to be zero, we consider the string has no mass. Okay, zero. Zero times A give you always give you zero. Then so that means T1 equal T2. Okay. By cutting the small part, by cutting a larger part, or you're cutting a small part in different positions, and then you can derive that the tension along the whole string have equal magnitude. Or just remember the result, it doesn't matter at all. And this is also the reason why, in most of the case, we will not label these two tension with two different symbols. We just relate them with the same symbol because they have the same magnitude. But because of they have different direction, so we also you need to use the arrow to represent the direction. So in this case also, okay, they have the same magnitude. But for exercise 2, so for this case, it's about the tension of the string across a smooth pulley. Then there's tension T1 and T2. It's not that easy to derive it, okay? But to derive these two have the same tension if the pulley is smooth. Uh, you're doing similar things as in the part 1. You're still cutting the small part of the string, and but in this case, there's not only two forces. There are also a no contact force, or just call it as nonration. They will talk about it next lesson, I think most likely. So also a nonration acting on the object by the pulley because they're in contact. So we skip this case. Okay, what you need to do is just memorize that these two have the same magnitude. Okay, we have introduced two forces. Okay, then the next two are the nonration and also the friction. So these two forces are the most complicated one. Okay, in the notes there's some exercise with the using the new calculus. You can just ignore it. Okay, ignore it. So let's go to the third force. This is called the non-reaction or reaction force or normal force or contact force or supporting force. So there's so many different names for it. But no matter how you call it, uh, most likely you have to include the word normal. So the normal in physics it also means perpendicular. So this force is always perpendicular to the surface, and Okay, like this one or this one. Yeah, it's always perpendicular to the surface. The nature of this force is a repulsive electrostatic force between two objects that are in contact. The reason behind is like this. So let's say these two objects, the block is placed on the surface. Uh, all objects are made of atoms. So let me draw some atoms here. Then the outermost of an atom are the electrons. Are electrons. So that means the object surface, uh, the there are electrons on the surface of the object. So when these two objects are in contact, so let's say they are closer to each other, or they're compressing each other, then at that time the electrons are very close to each other. Then same charge will repel. Electron and electron have the same charge. They will repel each other. And okay, repel each other. So these all of these forces are perpendicular. And then if you take the vector sum of all these kind of repulsive electrostatic force, then this is a normal force or the normal action acting on the object by the surface. And this is the reason why this force only exists when the two objects are in contact. If they are not in contact, there should not be a repulsive force between those electrons. Okay, so that's why we say that the magnitude equals zero when they lost contact. And why we say also why we say that the magnitude is not zero when these two objects are in contact. Okay, so let's stop at this page today. On Wednesday, I hope we can finish all different types of forces. Then we can go on to do some exercise on the forces of Olympic. Yeah. So this is really a large topic. I think we also need a week of time to finish this chapter. Yeah, most likely I think we can finish this chapter in the first week of August. So do you have any other questions? If no, let's meet on Wednesday. Okay, let's meet on Wednesday.